Welcome, I'm Brandon Mitchell, and today we're going to be talking about the state of the secure software supply chain. I've got my Twitter and GitHub handles here, and the Twitter, if you want to follow up afterwards, feel free to send me a DM or any questions over there. This presentation and others that I've given are over on GitHub, and I'll have a link to that at the end of the talk. So first, who am I? I'm a solutions architect with Boxboat. They're now an IBM company, and I help clients transition into the container ecosystem. In my downtime, I answer a lot of questions over on Stack Overflow, and by helping spread the knowledge about Docker through those answers on Stack Overflow and also presentations like this, I got added into the captain's program a while back. So let's dig in. Enough about me. I want to talk about what are supply chain attacks, but first let's have a quick recap. Attackers have a lot of different methods they can come and attack our environments. They can do the physical compromises, they can do phishing or social engineering attacks. All those are very common, in addition to patching or finding patch security holes that someone hasn't patched yet, something like the Equifax example. More difficult to defend against are attackers that use something like a zero-day or a malicious insider. So we're not going to cover any of that today. What we're going to look at are these supply chain attacks. Supply chain attacks I like to look at with a physical example like the Colonial Pipeline. And if you wanted to attack all the cars out there, instead of going after each vehicle individually, or instead of even going after the gas stations, or even going upstream from that and going after the pipeline that feeds those gas stations, what we saw with the Colonial Pipeline attack is they found a reused password onto the VPN interface of the billing system. And that wasn't protected anywhere near as much as the physical pipeline or all the individual gas stations collectively. So they found a nice, easy way to go in there and attack the system that had huge repercussions downstream for all the different users of that pipeline. So that's what we're looking for. They're looking for that soft upstream target rather than compromising the target directly. In software, what we see is this is going to look a lot more like instead of attacking the production server, they're going to attack the build servers or your upstream dependencies that you're pulling in from your project. And so the XKCD cartoon, I think this came out shortly after the OpenSSL Heartbleed attack. We're looking at just the one lone developer that is maintaining some project that everybody else depends on. So if you can attack that, the whole house falls down. So we've seen a lot of this in the news lately. I'm talking about this along with a whole lot of other people. Recently, we've seen dependency confusion attacks. Those were researchers that were looking at some repositories out there that they could see in code from different organizations that were sharing their code. Maybe they'd open source something, maybe they were demonstrating it in a presentation, but they didn't see the public repository for that code. So the researchers said, you know what, let me just go ahead and register this on a public repository because more than likely this is pointing to something the company has internally today. And what would happen if we do that? And what happened was the coding that pulled in all the various dependencies saw that there was a public repository out there for that code, and so it grabbed it from the public repo instead of the company's internal one. That was a bad preference that was unexpected, and so that was where they called it, this dependency confusion. It wasn't sure which dependency it should have pulled in, and it pulled the wrong one in. So that was one popular attack that came in a while back. Another set that we've seen recently have been attacks on tooling like NPM or similar package managers, where they're replacing the popular package that people have been using with a vulnerable version. They just release a new version that contains a Trojan or some kind of undetected vulnerability in there that the attackers can use. And maybe it's a long play attack. The developer out there always planned this and just waited long enough for enough people to use the product and then they turn bad. A lot of times what we're seeing is an open source developer that is just overworked. They got too much to do and they add a new maintainer. Someone comes along and just volunteers to help out, and after enough time they say, okay, we'll give you permission. And that was the whole goal all along. The person was finding some overworked developer and just volunteered enough until they got the access, and then they started shipping some bad stuff in there that just went unseen. The other way this can potentially happen is the developer themselves just gets hacked. It could be a targeted attack. It could just be they reuse the same password on two different places and they found the password they got into the Git repo and started submitting stuff. Additionally, what we've been seeing lately is the popularity around the SolarWinds breach. And that went after the build infrastructure itself. They found they found the build servers and were able to get in there and compromise those so that the build servers themselves signed the program, signed the result as that trusted vendor, and those were then distributed and deployed out to a lot of customers that deploy it in their environment It was signed, so they trusted it, and gave it access to all the different customer environments, gave it the keys of the kingdom, all the administrative access it needed because this was an administrative tool, gave the attacker a huge blast radius on their one attack. And a lot of people look down on SolarWinds and saying, you know, shame on them for getting hacked, but I honestly want to say if you've got something like a nation state going after you with an advanced persistent threat that doesn't want to be detected, can you really say for sure that you aren't already compromised right now with a similar attack? And I think a lot of us, we want to say yes, but realistically, the answer is probably no. And so as a result of that, we've seen the White House issuing an executive order saying we need to improve our supply chain security. That came with a lot of dollar figures behind it. And so because of that, you see pretty much everyone in the industry suddenly jumping after this and saying, yeah, this is something we want to help fix. Partially going after the money, but partially just because it is a huge issue that we all see and know that we need to fix. But this isn't new. This went all the way back to 1984. Ken Thompson was saying, how can we know that we can trust the compilers themselves? Because the compilers are compiling themselves. They're compiling the code and they give you a binary. If that binary saw that it was compiling the compiler, it could inject some malware and you would never know that the outputting binary is, you know, recreating its own vulnerability every single time it gets rebuilt. And it could also see that, hey, I'm compiling something like, well, back in the day it was the login command, but today it might be something like the SSHD daemon. And see that, you know, I'm compiling that. Let me just inject my backdoor into that as well. And the code looks fine. If you don't have anything wrong with the code, it is in that compiler binary. It is injecting that malware into all the different applications. These are very difficult problems to solve. What we are trying to solve, though, in the supply chain is how can we best harden our environment? And so to do that, we start by validating all our inputs. That's going to be something like a two-person rule on every commit. You got to have someone verifying and approving every one of these pull requests with you. You might have a scanner or some kind of other vulnerability analysis tool looking at all the different external libraries that you're ingesting and then copy those into your local environment in a secure way. You're also going to want to harden your build infrastructure. And this, you know, sounds, people throw it out there as if it's something like it's an easy problem, but it's not. It's solving that lower control problem. You can only go so far before you get to the point that you just can't solve it. If you're solving this with a hardened build environment, maybe that's a container image you lock down so it can only compile exactly what it wants to do. But now you need to make sure that your continuous integration system itself is secured. You need to make sure that the orchestrator that it's running that continuous integration system that is secured. You make sure the operating system that's running the orchestrator is secured. Every one of these things has a lower level below it that, you know, eventually you get to the point where you can't secure the cloud infrastructure itself. You're depending on the cloud operators to do that for you. And so you quickly hit a point where you can only go so far. You can only get this down to a certain turtle. Next area I want to talk about here is verifying the build process itself. And so how do we know that you did what you said you did? And then once you've done that, you need to sign your output. And so maybe that is a long-term signature or a transparency log, something there you can say, I did this, and other people can know that it's verifiable. You want to distribute your artifacts. A lot of times what we're looking at is trying to move this into container registries today. So instead of shipping the signature and SBoM and other attestations, other things we're going to talk about today, separately in a whole separate environment, can we merge those together with the containers into the same repository so they ship together in some way? So we're looking at different methods so we can do that. And lastly, the emission controller. None of this does any good if when we go into production and run our code, we don't check any of this stuff. And so the emission controller needs to go through there and verify that this has been signed, but it also has to do harder things. You know, preventing rollback and replay attacks and all those dependency confusion attacks. Maybe you have a malicious mirror out there you need to prevent. And if you handle something like revoking the key or an individual signature, that gets a little difficult, especially if you're trying to connect to some central revocation server. What happens if you can't reach it? If you can't, do you fail open? In that case, you're insecure. You're letting vulnerabilities potentially go through. Or do you fail closed? And if you do that, then you're going to create some outage downstream. It's one of these lose-lose. There's a bad answer on both sides of that. So this is the big picture. This is what we're trying to create. And what I want to talk about today is just what does the tooling look like? You know, there's a lot of tooling out there. And so we're going to go through this piece by piece. First step here is a software bill of materials. Think of this like your ingredients label. This is what goes into your application. It is going to be the name of your app that you're building, the unique version number so that you can track exactly what the application was that was deployed. but more importantly, it is all the different libraries and other components that went into your application. And so we got a couple convening standards out there. So SPDX came from the Linux Foundation. They were looking at licensing and adding security later on into that, because what they were concerned of originally when they created it was if we have something like GPL that gets injected into an Apache 2 project, that's going to corrupt the licensing and it's going to create some compatibility issues that someone may not have intended to do. So that was where they started from. Cyclone DX, though, came from OWASP. They are interested in security first and foremost, and so all the things that are required in theirs were security-based, and then they added licensing later on as an optional field. So what we're seeing is each of these things started with the mandatory things that they were focused on, and then started adding optional capabilities later on that people can or don't necessarily have to include in their SBoMs. And so we're going to see hopefully the merging of these two specs, or maybe one or the other is going to win out. Unclear right now, so that's still being played out. Importantly, you don't just want the SBoM on what you're creating. You want the SBoM on your build infrastructure itself. Were you building this with a potentially vulnerable compiler out there? You need to know about that. You're going to need the SBoM for every one of your dependencies, and then those dependencies need to include the SBoMs for their dependencies. This goes, iteratively through all the different chains, so hopefully you can get back to all the different environments that you're pulling in. Additionally, if you're running this inside of a cloud or a software as a service, you're going to want to make sure that you've got this for your runtime infrastructure as well. Are you vulnerable to something like a Spectre or Meltdown? You need to know that by looking at the bill of materials for the environment you're running your code in. So not just one SBoM, but a whole array of them for all the different places that you are potentially going to have to worry about vulnerabilities. And then you don't need to only generate the SBoM, but you need to use it. And to use it, you need to distribute it to the person that's going to use it. And so to do all that, we're looking at how can we push the SBoMs up to those container registries. And then those SBoMs, they're going to be pretty much static. They're hopefully reproducible, so every time you run the build, you should get the same SBoM out if you run it in the same environment. But the vulnerabilities that we can scan based on those SBoMs are going to change over time. And so we need a vulnerability scanner to look at the SBoM. And to do that, we need to distribute it again. And we need to make sure that we've got a scanner that can read it. And so that's an ongoing challenge that's still under development. Right now, we've got a lot of tooling to create it, but we don't have a lot of tooling to use it. So that's one of the key areas that needs to be developed still. Attestation. So one of the questions here is, how can we verify the truth and authenticity of what we do? How do we know we did what we said we did? In there, we've got a couple key tools that I'll look at right now. One of them is in Toto. They've got a syntax for giving an attestation for every step that you perform. And so you run your step, you sign it with your signature, say, I did this. Importantly, you include your inputs that you received and the outputs that you generated, and you've got hashes on all of these things. Then when you get to the final step, you can take all the different various attestations that you've received from all the individual steps and double check. Did all the outputs from the first step match the inputs from the second step, and so on? And that helps you detect if there's a man in the middle. Doesn't help you detect, though, if you have maybe a malicious build node, because you're on that machine with the private key that you can use to attest your code. That could also be the attacker that's on that machine with your credential to sign you said you did something good, even if you did something bad. So to solve that, we go to the next step here, which is Spiffy, which has the implementation of Spire. And what they're providing is some short-term keys to attested agents and the workloads that are running on those agents. And what does that mean? It means the agent itself is going to verify to the server with something like a hardware TPM or some kind of cloud API that I'm a node that should be trusted. And so it receives a bunch of credentials for all the different workloads that can run on that agent, on that node. And the workloads that are running on that node are going to contact their local agent and say, hey, I'm a trusted workload running on you. Can you give me my credential? And we're going to check, is this running with the right user ID, or if it's in Kubernetes, maybe check some labels or a Docker label, something like that to see, is this a workload that I trust on the machine? If so, yes, okay, give it that certificate. And now it can take that certificate or a JWT and use that in a tool like in Toto or something like that to say, I am somebody you trust, here are my credentials, and then we know that that workload is running on a trusted machine, hopefully a hardened machine, and we can verify those steps using the combination of tools like this. So it's not just one tool. We need to look for ways that we can integrate these things together to give you a strong environment. Similar project, Keylime here at the end, where we're going to talk about how to integrate TPM or something like that to give you a hardware-rooted cryptographic trust of a remote machine. And so what that is saying is, how do we know that remote machine is who we really believe it is? Well, we can use the TPM on that remote machine to give you that kind of hardware rooted remote trust. So we've now verified this is, we're running what we think we run. We made that claim of what we thought we did. Now we need to sign it. And to sign it, we need a couple things. One is we're going to need a key. And so to get our signing key, hopefully we don't have the signing key somewhere in the public that could be taken. And so to do that, we're going to look at things like Parsec, which gives these APIs to access the hardware security module or TPM or something like that. They've got these APIs that you can use to access that. The other one I've been looking at lately has been Vault. They've got a transit plugin, which kind of gives you a software version of this HSM that you're talking to. And you never get the private key directly. You just give it the data you want to sign. It comes back and says, here's your sign, the signed data or the public key for that if you need to verify that as well. And conveniently, it integrates on the Vault side with OpenID Connect, which you can use for authentication into Vault. That can be provided by Spire. So again, we're integrating these tools together to give you that hardened security. Another key tool here in the signing space, it kind of merges together a little bit of getting the key and also with signing the data is tough. They have a whole framework for how you can push software updates. They're big in the automotive and a couple other industries out there because they can prevent things like rollback and replay attacks and fast forward attacks by the way they've designed their key management and kind of a hierarchical set of keys. They've got one root key, but they've also got a target key. They've got a snapshot key to collect a whole bunch of targets together and say this is the current one. And then they've got a timestamp key that says this is a short-term thing that we're constantly iterating on, which helps them handle something like a revoke, some kind of revocation. You just update the new snapshot without that thing that you want to revoke in it. And then when the timestamp expires, someone has to get the timestamp on the new snapshot. So they've got this solution out there. That was used heavily in Notary version 1, but it wasn't the greatest implementation in version 1 of Notary. They had a few problems. And so coming out of there, we're now looking at version 2. What were some of the problems with version 1? Why they had to go to version 2? Well, for one, it was client-side enforced, and the onboarding experience on the client side wasn't the greatest. And so as soon as you try to pull your first unsigned image, you typically just turn this thing off just to be able to work with that unsigned image. And then you pretty much forgot to turn it back on again. In addition, it was giving you an alternate view of the tag. So as soon as the upstream vendor stopped signing something, if they stopped signing something, you would keep running the sign code, but maybe you're running some really old vulnerable code because it just says it's signed. It doesn't say it's been patched. And so you run this old version of latest that's been a year out of date, hadn't been signed since. Meanwhile, everybody else is running without the Notary v1 enabled, is running the latest and greatest patched image out there just because they pull latest at that point. Also in here, the other big problem, probably the biggest problem with version 1 that I saw, it was that it was trust on first use. We see that with SSH, but trust on first use, when you're talking about containers, you don't have that interactive user there to verify the remote machine they were talking to. And when you get into containers, you also see a lot of ephemeral environments. And those ephemeral environments mean that trust on first use is trust on every single use. So it doesn't matter who signed it, as long as someone signed it, we trust it. And that's not good to prevent attackers. So we're going to try to solve a bunch of those problems in version 2. We're also trying to move those signatures out of a separate Notary server and get them into an OCI registry so that they can be shipped alongside the artifact that we're signing. To do that, there are some challenges in there. We need to work on how to change OCI a little bit. I'll talk on that in just a second here. But yeah, it's going to be a challenge. But if we can do that, that means that we can now copy these artifacts between registries. That would be really nice because then you help support the disconnected environments that have their own local registry. This is still in the design prototype phase. I saw a recent Alpha 1 release from them, so they're trying to get some more visibility on what they're working on, so very much under development, something to look at. A little bit farther along in development is the Cosign project. That's under SigStore, originally started by, I believe it was a handful of Googlers, but they've the people running that one now, I think they've gone off into a company called ChainGuard. And what they're looking at is to push the signed data as a separate tag. And so instead of requiring the registry change some of the API calls in the registry, they're working within registries as they are today and trying to fit this into the model that's sitting out there. I feel like their 1.0 release was a bit rushed. They say they're stable, but they're still changing things like what do the signature contents look like. Maybe they want to change the signature envelope. Maybe they, don't have the best workflow for multiple signatures, so something there might still need to be developed. There's a lot of work still happening on this side, but it's probably far along than anybody else that I've seen so far. The other project coming out of that SigStore project was Recore. So Cosign can integrate with this to give you a transparency log. And they've got a public instance of this. It's not so stable right now. They've got no SLO at all, really. And they even have a notice on there that says they might periodically reset this. So if you're going to use it, you're probably going to want to self-host it. And so if you're self-hosting it, just realize you're self-hosting something that's still very much under development. So I did mention a little bit about the OCI. That's the way that we build and ship images today. They're a well-known standards body that are trying to maintain these specs for the image and distribution spec. And originally they were defining standards from what was already created. And so now they have the challenge of taking what was already created and trying to define a new creation on top of that. And so we've looked at the artifact spec of how do you push some of these things that aren't images into a registry. And it's not supported by a lot of registries with what they've got right now. They kind of extended the image spec to do that. So you got something that isn't really an image that needs to be pushed to a registry in the format of an image. And so they're looking at ways that maybe they can change that a little bit so it doesn't have to have that syntax of the config and a whole bunch of layers in there, but it can have a little bit more of a freeform syntax. And hopefully we can get some more support on registries when we do that. They're also working on reference types. So I mentioned some of the stuff in Node Review 2 is depending on this. What we're trying to figure out is, can we push something to a registry? You don't want to mutate the image because the image itself has that immutable digest on it, but you want to push a second object next to the image that has this reference back to your image. And so you need some kind of API you can query the registry and say, tell me all these things that have this back pointer to it. And that's going to be a little bit of an interesting challenge there. We're going to have to get registry support to add that functionality. And so that's still TBD, still under development right now. They have got a working group that they recently created, and so it'll be interesting to see what comes out of that. Or I think they've created a working group. It's still, I think that's in the voting stage right now. Also on this list here that we're talking about, OPA Gatekeeper. There are other kinds of admission controllers out there. There's even a specific admission controller just for security, just for verifying signing, but OPA has kind of got the ecosystem behind it. And they've got their own little language in there. You have to learn the Rego language. And they've got a bunch of stuff out there that's really stable. I listed on here not so much because of what they've already got, but what they're going to need to start adding for the image signing. And so there's going to be a lot of functionality that gets added into this as we get all these other projects finally production ready. We're going to need to see updates on the OPA side as well. I want to point out a few other related projects and groups. And one of those is the CNCF security tag. They've got a working group that based a lot of the work that we're talking about today on. Originally, they were created for a white paper that was talking about the secure software supply chain best practices. And so that white paper was looking at all the different best practices for, how do we secure all the build pipelines, what we're talking about exactly here today. But it was very high level. It was just, make sure you're using something to do some of the signing and whatnot. And so we need to look at how we can do an implementation of that. And so that's what they're working on now, is creating this reference architecture for what's involved in creating this secure pipeline. And that's where a lot of this content of today's presentation came from. Another big group in there that is playing in space is OpenSSF. That's from the Linux Foundation. And they are, the Open Source Security Foundation. That's what that SSF stands for. They've got a whole bunch of groups looking at how they can improve security. And I think some of those were based on when they had the OpenSSL vulnerability out there, the Heartbleed vulnerability. I think that got a lot of momentum on the Linux Foundation side that said we need to help improve the security of a lot of these open source projects. One last area to look at is Salsa. That comes out of Google. Google's been doing a lot of pushing from the security standpoint. And they are looking for how they can document the tiers for all the different projects out there. And tiers of the provenance and the security of that artifact that you're creating. And so they'll start with the first tier where you're just saying, let's verify that you've scripted your build and that you define all your dependencies. And then you go up to the fourth tier they've got, which is saying, let's make sure there's a two-person review on every commit, all the different code changes in there, that it's done within a hermetic and reproducible build environment. And I think there are a lot of people that aren't even close to that tier 4, but we want to document where you are between there. And so that's where we're looking from that. If we can start documenting all of our attestations and provenance of what we're creating, then hopefully we can start extending that to all the different dependencies we have. And so we can start to say, okay, this thing we're releasing to you, it comes with a tier whatever. And now we know we're only going to approve stuff that has a certain tier within our production environment. So that's what we're looking at getting to. So I said reproducible builds there, and that is a very key area. A lot of what we've been talking about is kind of the top line here, where we're saying just take a normal supply chain and harden it as best as possible. Make this thing so that no one can go through and change it if at all possible. The problem with that is there's always one of these lower turtles. Someone may still get into this. And so one of the things reproducible builds that we're looking at is just take that whole pipeline and run it a second time. Now, it's not so easy though, because one, you're going to have to build out a whole second infrastructure. So now you're doubling cost and time and CPU and everything else there. In addition, when you run that a second time, you're going to have something like a timestamp or perhaps some kind of externality in there. You do like an apt-get update in your package, and you're just going to start pulling the latest of whatever from outside. That's not reproducible. And so how do we make some of these things reproducible? It's non-trivial. We've even got things like host dependencies in there. You might inject a host name or some kind of build path or something like that into your code. None of that can be in there if you want it to be reproducible. So a non-trivial problem to create that. But if you do, and like I was saying, there's always this lower turtle problem. There's always you're depending on the cloud, you're depending on something else. If you can create a reproducible build environment that is a separate environment, managed by separate people, different organizations, so you have that isolation between it, you can know that if someone got into the build infrastructure and changed out your compiler, they would be able to do that in a normal supply chain. You might go through and say, yeah, that looks good. That's a green build. Give it a sign, deliver it. Everything looks great. If we can do it with a reproducible build, though, we can see that these two things are different. They were built by, something didn't match between the two outputs. There's something to look at. We need to figure out why these things didn't match. And in the open source world, that's even better if we can do reproducible builds there, because those builds might be completely different organizations, and it gives the attacker a really hard problem. They have to attack every single builder out there to make their thing undetected. So that's what we want to try to get to. That would be a great solution if we can get there. But like I say, it's non-trivial. There is a whole website dedicated to this, reproduciblebuilds.org. So if you want to check that out, please have a look for their project. They go through a lot of different steps you need to take to make your builds reproducible. And so it's a great resource. There are a handful of projects out there that are working on this. There's the Nix and Bazel and build packs and all these other things. The challenge I have looking at them is a lot of them, they don't use something like the Docker file. They require you to change your build to use their tooling instead of making their tooling work with your build. And so some of the stuff I've been looking at lately is, can we take something like a standard Docker file and make that reproducible? So that's been the challenge that I've been taking on my free time, whatever little free time there is to try to do this stuff. So it's a big problem. If you're interested in helping out, feel free to reach out to me. So let's wrap up. This was a lot of text, a lot of talking about what's involved here. It's really an attempt to hit on a lot of the popular open source tools that are out there, but I'm not covering them all. There's a lot more tools than what I've talked about here. And what I hope you've taken from this is that the secure supply chain, it's a complex process. It is not trivial to implement this. And we're going to have a lot of tools that need to be integrated together to try to make this happen. And if any one of those tools isn't working so great, you're going to have that XKCD cartoon where they just take out one little piece from the bottom of the stack and just cause the whole thing to fall apart. And a lot of these things are under active development. They're looking for contributors. And so hopefully this talk, if nothing else, maybe we got a few extra contributors that want to help out on that one. Also, unlike some of the orchestration and service mesh wars we've been seeing from other places, there are going to be a lot of winners coming out of this. And so, have a look, help out as best you can. So that's what I have to talk about. And this presentation, it's up on my GitHub repo. That QR code will take you there. And I hope that from there, you'll find something and you'll come and help out with the project. If you have any questions, feel free to hit me up on Twitter. If you're watching this one live, I've hopefully been answering some questions in the chat alongside of you. And if you saw any typos or something else in the repo here, feel free to open up a pull request over on GitHub. Thank you so much.